So to continue from last hour, from the previous hour, we found an equation for our radio link for the attenuation between two antennas, and with radio communication we usually use coherent transmission and coherent reception. So coherent antennas on both sides of our links, and in free space, so no obstacles, no lossy media, the equation we get the simple Friis equation, and we can express this Friis equation just with the obvious data of the antennas, the directivity of the transmit antenna and the area of the receiving antenna. Or for coherent antennas, we can replace all areas with directivities, or directivities with areas. So we can simplify this equation. Now, the only thing we don't know here is how to make efficient transmitting and receiving antennas. Because how to make efficient receiving and transmitting antennas, but we always consider that these antennas were designed for long distance communication. So R is very large. R is much larger than the dimension of these antennas. For R also applies the far field criterion, so the Rayleigh distance applies, so we are larger than the Rayleigh distance in all practical cases when you use this antenna. In fact, where we do need this Rayleigh distance, where we are doing measurements, we usually measure antennas in the lab at the short distance, because in the lab we don't have enough space. But the antenna in practical conditions we always used in the far field, and only in the far field all these quantities of the Friis equation, so directivity, gain, and also radiation pattern, all these things are only defined in the far field when the Rayleigh distance applied. When the distance is shorter than the Rayleigh distance, depending on the criteria we've chosen here, we cannot define not the radiation pattern, not the directivity, not the gain. They cannot be defined at shorter distance. This only apply in the far field condition. Under the far field condition, only this distance is applied. The issue is now that we don't know how to make these antennas. We didn't discuss that yet. So how to actually achieve this number we would like to have for our equation. In fact, in 100 years ago, in the first years of radio, antennas with gain were very difficult to make. The only exception was perhaps Heinrich Hertz, who used directional antennas, used so-called optical antennas, so converging mirrors for his experiments. But this at that time, these experiments were done at frequencies that were far too high for efficient communication. So they were done at about 400 megahertz, and at 400 megahertz, the range with the spark receiver was very, very, very limited. So what most people did in those years, they built quite inefficient antennas with no directivity at all. So if we look at what people did here, 100 years ago, they used long waves, so kilometers of wavelength for a few meters of antenna size. So this h over lambda was a very small fraction, further squared. So radiation resistance was very low. These transmitters were very inefficient because of losses, especially in the coil here. And also the production of radio waves with a spark plug was also an inefficient transmitter, not the inefficient antenna, but an inefficient antenna coupled to an inefficient transmitter. So everything went wrong here. People simply went to very long wavelengths because the spark, the electrical spark, was a much more efficient generator for longer wavelengths than for shorter wavelengths. They were much more efficient at lower frequencies. This was the reason why. But all these antennas are inefficient, so a short segment of wire is inefficient. Short compared to the wavelength is inefficient. But we can calculate it because in this case, this formula turns out very simple. There is no integral here. We don't calculate the whole integral. There is simply multiplication under these conditions. And similarly for the loop, The loop also, we calculate this for a loop with a small radius a, so the a prime, the area of this loop, is very small compared to lambda squared. Also here we have a prime divided by lambda squared, and all this is squared. So also here we have a very small radiation resistance. We had milliohms here, we had micro-ohms here. Perhaps the loss resistance of this coil, of this inductor, is in the range of ohms. So that's the reason for the very poor efficiency of this antenna. So now we have to look whether we are able to do anything better to fit our equations. These equations are valid, but now the engineer has to build an antenna with useful gain. Some useful gain, some useful efficiency, some useful directivity. That's the engineer has to do. What we can do is actually use a longer wire. A longer wire that's perhaps 1/2 of the wavelength long. In fact, Heinrich Hertz already used such a transmitter. Heinrich Hertz already used such a transmitter because his spark plug, the impedance of the spark plug in between here, the generator was a spark plug, was very low, so it was well suited for this half a wavelength long dipole with no electrodes on the ends. There were no electrodes on the end. This was made of thin wire, and thin wire, if its diameter is much smaller than the wavelength, then the current distribution of such a piece of wire is no longer constant, but it's a standing wave. Standing wave for the standing wave defined by the distributed inductance and distributed capacitance of this wire. This is near field. This has nothing to do with radiation. If the wire is thin, these near field effects will be much larger than radiation, and they will these near field effects will actually define the current distribution here. And the current distribution on a half wavelength dipole is just a cosine. A cosine of wave number times z prime is the coordinate of my wire segment. How do I calculate the radiation of such a half wave dipole? The radiation of such a half wave dipole, I simply I have already solved this problem, the radiation of a short segment. I have this solution written up here if I consider radiation only. Radiation only is considered here, so from the previous equation I had here, I take this solution here and I only take this term. For the electric field, I only take this term from the solution here, and this is already calculated for a short section. But now, when I have a longer wire, I simply have to integrate along the wire and see what is changing. And when I move this section along the wires, the angle theta prime changes, so 1 theta prime changes, sine theta prime changes. The distance changes, r minus r prime is the distance, this changes, and changes both in the denominator and in the phase in the numerator. But we know from our previous example that at large distances, phase is the important property. Phase changes are the only ones that are important for the sum. Amplitude changes are not that important. And if I look now at the derivation of the far field, this dE, I can simplify this 1 theta prime with just 1 theta. This is just amplitude changes. I can simplify the denominator with just r, because r minus r prime is almost r in the denominator, is just amplitude. But the numerator contains the phase, and in the phase I should consider this r minus r prime. I should consider a better, I should use a much better approximation for this one. It's free space from the origin, plus this correction term here for the phase. This correction term then depends on the cosine of theta, and depends also on the position z prime of this. So I should not neglect this correction. This correction is an approximation for this. Of course, I get the whole electric field by integrating these short segments along this wire, and considering the current distribution on this wire, which is E generator. E generator is actually the maximum because the I put the generator in the maximum of the current distribution here. Cosine times this cosine, this exponent fraction. Oh, J is missing here. JKR, JKZ. J is missing here. Now I saw. J is missing. So if I have a complex exponent function and the cosine, I can also rewrite the cosine as two exponent functions, and this is integral can be solved quite easily, and this is the solution. The solution that of the integral itself has sine squared in the denominator, but multiplied by this sine squared, I only have one sine squared in the denominator. Of course, J here, this is a complex exponent function with J is missing up here. J is missing. So the radiation pattern of my antenna is actually cosine of pi half times cosine theta divided by sine theta. This is the new radiation pattern, which is nothing special really. This radiation pattern doesn't really differ much from the sine theta we had before. But I have to make accurate calculations, so I have to calculate the directivity. The directivity, I should integrate the square of this one here, squared, and I should get this integral. And with this integral is actually an integral that cannot be expressed with standard functions, so I have to calculate this integral. I have to calculate it, and its value is 1.22 approximately. So trying to calculate the directivity is 4 pi. 2 pi is integration over phi. So it's just 2 divided by this value of this integral is 1.64 or 2.1 dBi. More important, if I go and calculate the power flow out of this antenna, and I calculate the radiation resistance is simply the radiation resistance of free space, 377 ohm divided by 2 pi is 60 ohm, times the value of my integral. This is 73.5 ohm, 0.1 ohm. So a half wave dipole has some directivity. It is not particularly good, this directivity, but has a very useful radiation resistance. This radiation resistance, 73 ohms, it's something that can be easily matched to any generator. This radiation resistance is much larger than the ohmic resistance of the wire. So such an antenna will have a high radiation efficiency. Usually 99% is a typical figure for a half a wave dipole. So this is antenna I can make, I can build in my lab, I can use for measurement, and that is the reason why this 2.15 dBi, this figure is very useful for me, because I can compare other antennas, unknown antennas, to this dipole, and I just subtract the directivity of the 2.15 dBi, or this will be the directivity of the unknown antenna. The dipole has 0 dBd, 0 decibels, compared to a half-wave dipole, another half-wave dipole. So that's the reason why of the importance of this figure. But this is actually, I can build in my lab. It is quite efficient, this antenna. It can be used in many different ways. So this is one of the antennas that works. Where is the trick here? The trick is to have the length of the antenna comparable to the wavelength. I could make this antenna a little bit longer, say one wavelength still provides useful data with much higher radiation resistance, but longer than one wavelength, the radiation pattern of such antenna is spoiled. So the radiation pattern gets many side lobes, many very disturbing side lobes, so we usually don't build dipoles longer than one wavelength. Half a wavelength is the most typical example. Now, dipoles are useful to build many antennas, but still there are antennas that are very difficult to handle in this way, like an aperture. What is an aperture? An aperture may be this area here of this aperture may be covered with dipoles. And these dipoles have their feed structure, their wires feeding them, so it's very complex to get the current distribution over an aperture covered with dipoles. Could be covered also with something else. This aperture could also be an aperture of a horn, of a waveguide horn. Which currents do I have to count there? That's a very difficult problem to be solved. So the best thing is here to use the Huygens principle and replace all sources with replace the field here on this aperture with sources that are built on this area, and these are called Huygens sources. And for the Huygens sources, I can calculate the whole power radiated from such an antenna by integrating all the sources and considering also the distances here, the phase shifts. Of course, phase shifts are important at large distances of all these Huygens sources that themselves have a radiation pattern of 1 plus cosine theta squared, because we are at the power here. So this is an exact solution if we know the field distribution of such an aperture, and this aperture is much larger than lambda squared. Then this formula is quite accurate, because if it's smaller than lambda squared, we have many edge effects here, so it's no longer that accurate. How do we calculate the directivity of such an aperture? Here we know what is the power radiation pattern here. We have, if the maximum of directivity is on the z-axis, this is not necessarily true, but it is usual to have the maximum directivity on the z-axis. Then this integral for the maximum power flow, its maximum power density, is very easy, because sine theta is 0, so these two terms here vanish, and cosine theta is 1, so this becomes 2, squared is 4, it cancels out to 2. So the maximum power density is easily calculated. However, for the whole power radiated by this aperture, we could do it that in far field. We could integrate it with far field, but integrate in the far field such a radiation pattern, it's very difficult mathematically. It's much easier to integrate the power that's flowing through this aperture. We just integrate on the surface of the aperture. Again, the pointing vector here, we integrate on the surface, and this is a very simple integral usually to do. So our directivity, if I calculate it from these two formulas here, pi over 4 pi squared, this is the average power density. If I calculate these things here, I get this simple formula for the directivity of an aperture. The directivity of an aperture, you see here, can be made arbitrarily high, arbitrarily large, by increasing A. By increasing A, I can increase the directivity. So I know the trick how to increase the directivity. Without doing many complex things, but just this simple. How is this directivity increased? This directivity is increased because these two terms here actually narrow the beam radiated. The beam is maximum in the z-axis when these two are zeros, but this beam will decay off axis by these two terms here. These two terms integrated, they get a result in the form of sine x over x, or j1 of x over x if it's circular geometry, if it's circular aperture. So I can make my beam arbitrarily narrow by increasing A, by increasing the surface. The most obvious example of this formula here is a constant distribution. So I have a constantly illuminated with the same phase, this aperture here, constant illumination with the same phase, so this is constant. And now D is simply 4 pi over lambda squared times A. The formula we assumed here, we said here that we have this formula, we didn't really explain where it came from. Now we have an exact explanation. So this can be, this field here can be, the radiation of the Huygens sources on this aperture can be calculated accurately, and the formula falls out. This formula falls immediately out. If the illumination is not uniform, or if it has a phase error, then we have to calculate the integrals we have here. We have to calculate both integrals, and the directivity will actually be smaller. Will be smaller. Why? Will be smaller because this sum, the sum in the denominator, is all sum of positive real numbers, while this sum here is a sum of phasors, and phasors may not add in phase. So the effective area may be smaller, the aperture efficiency may be smaller than 1. This eta 0 is called the illumination efficiency of our aperture. It has nothing to do with power loss, with heat. Please do not mix this one with the efficiency we had over here. This efficiency actually means that this light bulb is producing mainly heat and little radiation. This is radiation efficiency. While this one here, illumination efficiency that we have here, this illumination just means how uniform is this E on this aperture. If it's not uniform, it's still all being radiated. But it's not radiating with the directivity we could obtain with a uniform illumination of this efficiency. So the aperture, and a correctly illuminated aperture, is actually the way to go to get directivity from an antenna. This is the solution here. So what can we do? What are the practical solutions? We've already seen this. We illuminate our aperture with many here half-wave dipoles. We can do this. We have to feed them in phase. We have to carefully check the lengths of the lines to have them all in phase, with the correct phase, fed in the correct phase, and we can build a phased array. This is one possibility of illumining an aperture. The other possibility is what Heinrich Hertz did 150 years ago almost. So Heinrich Hertz, he used a converging mirror. So this was an optical solution actually. He put his half-wave dipole in the focal point of this converging mirror, and this aperture, the aperture of this mirror, is now illuminated with a wave with a constant phase. It is not perfectly constant amplitude, but perfectly constant phase here. So converging mirror is certainly an optical solution to the same problem, and there are many possibilities how to make this converging mirror. If it's just a single mirror from a point source to infinity, this should be a parabolic mirror. There are also other mirrors possible, antennas with many mirrors like Cassegrain or Gregorian telescopes. All this can be borrowed from optics, provided that the mirror is quite large compared to the wavelength. A converging dielectric lens can perform the same function as the mirror. It can also transform the radiation of my dipole in all direction into almost parallel rays or narrow cone in the infinity. So a dielectric lens is also a solution. One possible solution is also, here is it's a horn antenna. Now, for simplicity, here I drew only a transversal electromagnetic horn that has a TEM line made from two strips of conductor, and then these two strips are spreading out to form a TEM horn. Now we know the field here. It's approximately electrical field lines vertical, a magnetic field lies horizontal. If we do this horn shallow enough so that it slowly opens up into an aperture, now this aperture here is illuminated by the same field pattern as provided by the generator in my here strip line. So even with the horn, I could spread out my field to a larger aperture, but here I do get phase errors because I have spherical wave fronts here. In order to avoid this phase error, this horn should be long enough. How long? We had already the solution here. It's the same Rayleigh distance. The horn should achieve, if we don't want phase errors, if we want to avoid phase errors, we have to build the horn long enough. This horn is also so-called the idiot antenna because the horn always radiates. Horns always work. This is an antenna that always works. But this antenna may become very large because the radio distance may be very large, and we may have to build very, very long horns. Not that for a given aperture, the horn may become very long. For instance, for television reception, satellite television reception, a dish is nowadays around half a meter diameter. If we were building a horn, it would be half a meter aperture for 10 meters length, and that becomes a huge antenna. It works, but it's just unpractically large. What also seems impractical, this converging dielectric lens seems impractical because with radio waves the wavelength is large. So also this lens is very large. This is a huge amount of dielectric here. Tons of dielectric for meter wavelength. And that is very large, and it's also very unpractical. It is practical in optics where the wavelength is small, but in radio where the wavelength is large is very impractical. And here we come to another idea with antennas: build artificial dielectrics. Artificial dielectrics made from differently shaped pieces of metal, like metal rods. I can make some space behave as a dielectric with an effective dielectric constant, effective permittivity, relative permittivity, larger than 1. This is also called a slow wave structure. Slow wave because the waves are slowed compared to the free space. I can also build a diverging lens with somewhat larger than half a wavelength or metal rods. So I can also build a diverging lens, and with this two lenses made of artificial dielectrics, I can also make a directional antenna. So the radiation is actually increased in the direction of the converging lens, and it's decreased in the direction of the diverging lens. So that's the trick to make antennas. Maybe the next picture I can show you this in more detail. So this was the really new idea about antennas. Parabolic mirror is known from optics, lenses are known from optics, but artificial dielectrics are difficult to make in optics. And the first one to do to build such an antenna was Shintaro Uda in 1926 at the University of Tohoku in Japan. This antenna was actually not named after Uda. It was his article was only published in Japanese, and few people read that. It was only when his supervisor, 3 years later, his supervisor Hidetsugu Yagi, published this antenna and showed this antenna in the United States and published the article in English. So the antenna is frequently called today Yagi. More seldom is called Yagi-Uda, but unfortunately is never called by its inventor Shintaro Uda. This is really Shintaro Uda, and this is something really new that happened with radio antennas. This is really new because this didn't exist in optics. It could not be made because these rods in optics would be very small. The rods had to be slightly shorter than half a wavelength to produce a relative permittivity larger than 1. If we want both polarization, we should put crossed rods. But the mass of these rods and the volume of these rods is much smaller than the mass of the dielectric. So this is something that can be built also for meter wavelength, also for decameter wavelengths. For short wave, such antennas can be built. If we need both polarization, we have to use crossed rods for this slow wave structure. We can also use wire loops with the circumference of about 0.9 wavelengths to make a slow wave structure. They may be of different shapes. They may be circular, maybe square, maybe triangular. This is usually called a loop Yagi or a quad Yagi or something like that. Always Yagi after the supervisor of Shintaro Uda, but he did not actually invent the antenna. In fact, Yagi himself says in his article that it was Shintaro Uda, the real inventor of this antenna. So he was correct, Yagi was correct, but other people were not correct. What happened in practice is that this antenna immediately had a military purpose. For the first radars built in the period between the First and Second World War, and everyone in the period between the First and Second World War built radars for this frequency range. Not just the British, Also Americans, also French, also Italians. Even in the Soviet Union, they built radars with such antennas made by Uda. And of course, since the Japanese were their enemy in the First World War, they didn't want to name the antenna after the enemy, and they just called this antenna a beam antenna. So a directional antenna. They called this a directional antenna, a beam antenna. But the expression beam only means artificial dielectric, a slow wave structure invented by Shintaro Uda. There were other slow wave structures invented further on. The most interesting is the helix. A helical wire with the correct parameters is with the circumference, so the length of one turn about 1 lambda, and the spacing of 0.2 lambda. This thing behaves as a slow wave structures invented by John Krauss in 1946. And also discs can be used with such antennas, and discs are quite advantage. Discs with the diameter of about 0.3 lambda act as an artificial dielectric, and this was invented by Simon and Weil in 1953 in France. These were two Frenchmen that invented such a disc Yagi. The Americans called it disc Yagi because they are unable to read French here. So they invented their own name, but the Americans never really loved this antenna, though it's perhaps the best choice of all slow wave structures. It's a disc structure. If you have, it is most wideband, it provides the highest gain of all slow wave structures. So this just to tell you the detail of antennas with artificial. This is something new. Something new with antennas. Converging mirror, a parabolic mirror that's taken from optics. That's already known. Horn, it is something new. The TEM horn is something new in radio waves, but the horn already used by already used in 1895. The first horns were made by Jagadish Bose in India. But he didn't even know how these horns work. But the horn antenna is a very inefficient and is very large. Why? This is very efficient. This is very efficient. Very little material for many decibels of gain. So this is something new, and this is something should be remembered, and Shintaro Uda should be remembered. It's interesting to learn that both both Uda and Yagi survived the Second World War and lived for many years on, so they both died at a very late age, in over 80 years old. So they did, while Japan had lost the war and had many casualties, but both Uda and Shintaro survived the Second World War. Now the next thing we have to deal with propagation. So we have antennas that actually radiate. Antenna radiates power to be received by receiver. But how much space do we use here in between? Free space. How large this free space has to be so that we can call it free space? And this also, how much space is used by electromagnetic radiation. Not just electromagnetic radiation, the same reasoning also applies to other kinds of waves, like sound radiation. These are mechanical waves. Also applies the same reasoning, and the reasoning of the Fresnel ellipsoids. If we put our transmitter and our receivers in the focal points of our ellipsoids, then we can draw ellipsoids around these points, and we select ellipsoids that their characteristic distance is L1 to the surface of the ellipsoid is equal to the shortest distance, dtx or drx, plus n times half wavelength. This is the definition of the Fresnel ellipsoids. And we are going to see later on that most of the power is transmitting in the first ellipsoid. This question is not exact. This answer is not exact. It's not just in the first ellipsoid, but most of the power travels through the first Fresnel ellipsoid. The cross sections of the Fresnel ellipsoid are called the Fresnel zones. Row 1 is a circle, while row 2 is just the space in between row, while the second Fresnel zone is just this green area, and the third Fresnel zone is just this yellow area here. All Fresnel zones have the same surface. All Fresnel zones have the same surface as the Fresnel zone, as the Fresnel zone number 1, the first Fresnel zone. And here I calculated a few examples for radio broadcast 100 megahertz, microwaves 10 gigahertz, light 600 terahertz, with a distance from the transmitter of 20 kilometers and 10 kilometers to the receiver. 100 megahertz is 3 meters wavelength, so 3 meters wavelength here is 140 meters, the radius of the first Fresnel zone, quite large at low frequencies, but at microwaves at 100 times higher frequencies, it's 10 times smaller, it's 14 meters. And at light, it's just 6 centimeters, so it's very small, the radius, the diameter of 12 centimeters of the first Fresnel zone. So the Fresnel zone shrinks as the wavelength becomes shorter here. This is now a little bit without proof, but we shall try to find a proof for this statement that most of the power travels in the first Fresnel zone in the next slide. This is actually the formula. The formula simplified for the Fresnel zone is much smaller than the distance from the receiver and distance from the transmitter. Then we can simplify this equation here in the radius of the Fresnel zones. On the next slide, we try to calculate here the diffraction loss over an obstacle. So we have a transmitter, we have a receiver, and we have a mountain ridge in between the two. A mountain ridge, that's also a knife edge obstacle. This is simplified to a knife edge obstacle. And now we have to calculate the power diffracted over this crest of this mountain ridge. How do we do that? In this plane x and y, here we put our aperture that goes over the x-axis from h to plus infinity, and over the y-axis from minus infinity to plus infinity. We take this xy plane as the plane of our aperture, but our aperture is partially shaded by the obstacle. We calculate the field, so I said that the aperture goes from h to infinity in the x-axis and from minus infinity to plus infinity on the y-axis. We calculate here the distance with all the simplifications we could make here, the simplifications for small offset compared to the distance, so that these cosines are almost equal to 1, so that the horizontal distance in the attenuation is almost equal to 1. The only important thing is the phase. The phase is accounted here, up here. The phase is accounted here, and the whole equation is now normalized to the first Fresnel zone, the radius of the first Fresnel zone. If we calculate the integral from minus infinity to plus infinity of these small sources on our aperture here, we only are left for the vertical integral, and this vertical integral is here. This is one of the two Fresnel integrals here. Fresnel integrals were invented by Auguste Fresnel more than 200 years ago to explain the propagation of light. Okay, this is the solution of the integral here, and I also replaced the limit of the integral to have the integral much more easier to calculate, and calculate this limit here. If we calculate now the loss of such an obstacle, we have to take 20 times the logarithm of this of the absolute value of this thing here, because the Fresnel integral gives a complex result, and this is also a complex number, so we calculate the absolute value, all the complex quantities shorten out. This is 1 over square root of pi times this integral, and the absolute value of this integral, because this integral is a sum of phasors down here. And the exact solution is the blue line here, and the obstacle height is depicted as the ratio of h over rho 1. So the ratio of h compared to rho 1, so this is minus first Fresnel zone, this is plus first Fresnel zone. If we go to the previous picture, this is from here, from minus rho 1 to plus rho 1 here, but in Cartesian coordinates. The exact solution has some wiggle here. And the field really starts, the attenuation starts increasing while the signal starts decreasing while we cross the minus 1 boundary. We get exactly half of the field, this is minus 6 dB, when the obstacle just touches the line connecting the transmitter and the receiver. So this is minus 6 dB. And further on, we have this curve that's decaying all of the time. So, in order to have almost free space communications, this h should be minus rho 1. Minus rho 1, well, here it's almost there. We have also an overshoot here, but this overshoot is small for practical reasons. It's slightly more than a dB here, so this is really small. The problem is this thing here. The problem when the diffraction loss increases, the signal decreases down here. And rather than calculate this integral, this cannot be expressed with standard function. It has to be evaluated on the computer with numerical integration. We could use an approximate formula. An approximate formula minus 16 minus 20 times logarithm of 10 of height of our obstacle divided by rho 1, the first Fresnel zone. So this formula is only valid for this section here. And in effect, here I plotted the approximate formula versus the exact solution. You see the approximate formula diverges from the exact solution below rho 1. But above rho 1, it's quite accurate. So it's a good prediction what is going on. So we could predict here what will be the diffraction loss of such an obstacle. The diffraction mostly takes place on the crest of this mountain, and that's where problems arise. So this is the mathematical formula for a geometrically exact obstacle, an exact knife edge. If this knife edge is not exact, if I have trees planted on this mountain crest here, if I have trees here, I have even less diffraction. So I should consider that this formula is perhaps valid up to 3 or 4 rho 1, but beyond this, the formula is still valid for an exact obstacle, but not for a real obstacle that has many artifacts here on top, like trees, like a round hilltop, not a sharp hilltop like here, a rounded hilltop. Then this formula is. So I know about how an obstacle. Of course, to know the effect of this obstacle, the important thing is to compare its height above the connecting line, the direct connection between the transmitter and the receiver, compared to rho 1. Everything goes compared to the radius of the Fresnel zones. Here. Even when we have all Fresnel zones clear, the result may not be that simple. This is the result where this direct ray from a base station to a pedestrian user here is unobstructed. This direct ray, no Fresnel zone lines in this direct ray, and there is no obstruction, and this pedestrian should have a good signal if he can see the base station. The problem here is the reflection of ground, the reflection gamma here of ground. And if I take the typical values for a GSM phone, so 30 meters tower height, 3 kilometers horizontal range of the and pedestrian height 1.5 meters, so the pedestrian usually keeps the phone on his ear, so or her ear, and this 1.5 meter above ground. I have quite a strong reflection off ground. And this reflection from ground is almost specular. Why? Because the Rayleigh conditions, the Rayleigh roughness, should be smaller than wavelength divided by 16 times cosine. Now cosine for this figures here is 0.01. So this is about 6 lambda. For the data given here, this comes up to about 6 lambda. So 6 lambda with 33 centimeters wavelength, this is 2 meters. A roughness of 2 meters. Well, streets in towns are usually have a roughness of less than 2 meters. Otherwise, cars would fall in holes in the streets. So there are no streets are much flatter than this, and I have specular reflection from streets or from grass meadows. Grass is also practically a specular reflection for the GSM phone. And this reflection is very strong and it's out of phase. For very flat, very shallow incidences, so theta close to pi, this incidence is this reflection coefficient is almost -1, and it's polarization independent. We get -1 both for vertical and horizontal polarization. While for for steeper incidences, the Fresnel formulas apply, and of course the Fresnel formulas give different gammas for both for the vertical and horizontal polarization. The cross-section of the first Fresnel ellipsoid is the first Fresnel zone. This Fresnel zone is quite large, but within this Fresnel zone, the Rayleigh roughness criterion applies. So this Fresnel zone is usually flat, completely flat in a town, whether this is a street, a paved street, or a grass meadow or grass park. We also always have this flat region. In this case, if we calculate the interference between the direct ray and the reflected ray, it has a sine function in between. But for small arguments, the sine function is almost equal to the sine of a small argument is almost equal to the argument. So we could simplify these things, and what happens here is now that the out of our formula, the wavelength cancels out. We only have the height of the transmitter, the height of the receiver, and the signal decays not by d to the squared, but d to the fourth power. So because of this reflection from ground, the signal decays much quicker. And this is actually useful for phone companies, because in this way they can predict where the signal decays, and they can reuse the same frequency channel in another spot without causing harmful interference to these communications from the base stations to the girl here with the mobile phone. It's interesting to notice that they've made many phone companies made many measurements in urban environments, because there most of their users walk around, and they get a similar formula just from measurements: power of the transmitter, gain of the two antennas, a proportional constant here, and this actually depends on the town. This alpha depends on the town. Squares of both antenna heights, and d to the minus n power when this n is between 3 and 5. This is what the measurements give. The theory for the reflection of ground gives d to the fourth power. So these measurements actually fit this formula very well, with some corrections for the particular town, particular kind of buildings, because it's not the same if your building is made of cardboard or if your building is made of steel reinforced concrete. So that's quite a difference here. So this is a significant amount of loss here, d to the fourth power, but it's actually useful for the phone companies to make more money from the same frequency spectrum they have allocated. So yet another effect, we cannot cover all the effects of radio wave propagation in this lecture. Another effect is the atmosphere, the attenuation inside our atmosphere. The attenuation inside our atmosphere is mostly made of nitrogen, some oxygen, and traces of other gases. What comes out, this is the curve. We see that below 100 gigahertz almost nothing happens. Below 100 gigahertz, the atmosphere is rather transparent, except for this oxygen absorption band. In fact, we have a water vapor absorption band even at 22 gigahertz, and this was discovered by the Americans in the Second World War. They built radars operating at 22 gigahertz, and they could not see the Japanese aircraft, at low latitudes in the Pacific Ocean with high water vapor content because of the water vapor absorption. So the American radar did not work for this reason here. Oxygen is always present in the atmosphere. You cannot get rid of that. That's 14 dB per kilometer here, or here almost much more. So more than 100 dB for a zenith zenith attenuation in the atmosphere. Which gases are important? As I said, water vapor is this green for tropical, blue for tropical, green for moderate, red for polar regions. We have oxygen, that it's important here, at least later it's less important here, the oxygen. Nitrogen is almost unimportant. Ozone is somewhat important. If we cross the ozone layer, say for space communication, then ozone becomes a problem. So we can no longer consider the atmosphere to be transparent above 100 GHz. Below 100 GHz, there are pretty wide ranges that are still useful, but above 100 GHz, the atmosphere is no longer transparent. There is not just the loss in the atmosphere, that's also another effect. Another effect we have here, besides loss, if we have loss, we also have a refraction index. I cannot cover the whole refraction index. I'm only going to give here a rather nasty example of what can happen with the refraction index. So the refraction index always decreases with altitude. Decreases with altitude because the air becomes much rarer at the altitude. But the temperature also decreases with temperature, but what the nasty effect is if we have temperature inversion. Say if we are in a closed valley and we have fog. What is a closed valley and what is fog? It's a question. Over plain region, this region may extend 1,000 kilometers. In Slovenia, like in the mountains of Slovenia, this is just a few tens of kilometers. We have cold air in the closed valley and we have warm air above. The warm air has a much lower refraction index than the cold air, so we may get refraction on this boundary, refraction on the two different refraction indices, and this refraction index causes additional attenuation. Worst of all, we may also have total reflection on this boundary, if this is not drawing, not to scale. If we have total reflection here, then we may get connection between these two antennas that otherwise would be shielded by this small mountain in between. So we may have dropouts of some radio links that before operated correctly, and we may get new other links that mainly cause interference, that these links only happen when we have total reflection of this boundary. So the change in the refraction index in the atmosphere, because this thing is much broader here than it's high here. This drawing is not to scale. This should be much longer here. Should be much longer. So this all these incidences are very shallow. If the incidences are very shallow at very shallow angles, then even small differences in the refraction index cause huge differences in the propagation of radio waves. So temperature inversion, which may be such a bad problem when these things really happen. But we also have refraction. We have continuous refraction just in the undisturbed atmosphere, in the well-mixed atmosphere, and even that refraction has some effects on radio waves, but it's too much for today's lecture. It's too much to explain for these things today. We also have may have additional loss on on rain or snow because of scattering on raindrops or scattering on snowflakes. We may have many other effects, and of course something we didn't talk on this picture here. We have similar effects, a total reflection, also in the ionosphere, much higher. So that's 100 times or 200 times higher than this picture here. Up here we have the ionosphere that may also cause total reflection, then may also cause refraction at particular frequencies. So the ionosphere should also fit on this drawing, but That's too much for today, and that's too much for a course on communication electronics. For us, it's important to understand the basic limitations here. So next time we are going to go to more electronic items. For the next lecture, we have to see what kind of devices do we need to communicate. And the most difficult devices to build are those performing nonlinear functions and those performing amplification of the signal. So we need both to be able to make this transmitter and receiver connected to our antennas. We also need that for optical fibers. We also need that for cables. So next time we start looking at the devices, and then we are going to look at the different effects in these devices. So this was an introduction. But still, antennas are part of electronics. Optical fibers are part of electronics. Cables are also part of electronics. But we started our course with the transmission medium. Now then that we know the requirements of the transmission medium we have, that's also electronics, we should see at the actual devices, at the actual electronics we need here in our communication. What we need at the transmitter, what we need at the receiver side. We should look at the electronics and the limitation of these electronics, and we start next time with semiconductor devices.